The height of the students in a class follows a normal distribution with a mean height of 165 centimeter and a standard deviation of 5 centimeter.
Yes, sir.
So we are not talking about the students present. There are so many students present and we're not interested to count the head. We are not interested to count all of them here. What we want is whatever number of students are present here, we want to pick up only one. And there is a little bit variation in their heights because the height of the students follows a normal distribution. That means there must be a little variation. That is what normal distribution is. There is not a lot of variation among their heights. Now we'll pick up one of the students and will measure height. Because there is a little bit variation, even before finding the probability, we have a rough idea that if we check the height, if we pick up one and check the height, then height will be around 165. The difference among their heights is not quite large here. So we'll not worry about that. We'll make it sure that the answer will be around 165 only. Okay. Now here we select one. If you select one, you have to measure the height and you will see that the height of one student is around 165. But in the question, it says find the probability that this will be greater than 167. Never mind. Let me write this. X first, then probability. X is height of the students. That's all. Height. X is height here. It's a continuous random variable. Height of, I'm not writing more. You need to find the probability that X is greater than 67. 167. This is what you need to find. And that will be equal to, because you know the probability distribution of X, normal 165, standard deviation of 5. So we'll write this way. Then I need to find the probability that X is greater than 165. So I'll subtract 165 from both the sides, 167 minus 165. And then that will be equal to, and I need to divide by 5 also. This will be my standard normal, and this is 2 divided by 5. That is probability that Z is greater than 0.40. So this I have to see from the actuarial table. Why it's behaving this way, improper? I don't know. Let me see anyway. We have to increase it or what? 100%. We'll make it 100%. This is standard normal distribution. So you have to say this. Can you tell me this one? Z is greater than 0.40. Because you will see from the table, probability Z is less than 0.40, not greater than. We can see greater than from the table. So I have to transfer to this one. 1 minus probability z is less than 0.40. 1 minus 0.65542. So that will be 0.34458, right? So this is the answer, 34%. There is a 34% chance that you can say around 35%, the height will be greater than 167 centimeter. This is the probability. Because there will be many less than 167 centimeter, 164, 162, 165. Okay.
Okay, sir.
So height doesn't matter. There is a little variation anyway. Ultimately, the thing is you are picking up one.
Yes,
and
sir.
you don't know even how many students are there. Now
Yes.
in part 2, if you see, we'll pick up many. Suppose we'll call 50 students
Okay.
and we'll measure only their heights and
Okay.
then we'll send them to the class. Let them go.
Okay.
Suppose there are 10,000 or 20,000 students, we'll not count the total number of students. We are interested in the height of the 50 students only.
Okay.
Then we'll be able to know their mean height also. Now, before finding anything, the question is, what is the probability that the mean height of the students is greater than 167 centimeter? So if I write this here, I will just replace x by x bar. That is the only thing. If I write this is x1 plus x2 plus x50 divided by 50 greater than 167. Can you do this problem? All are normal distribution, all follow normal distribution, that's fine. But then it's very tough to find, it's very tough to do this kind of a problem, right?
Yes, sir.
So we'll use central limit theorem.
Okay.
Yeah, if you apply, it will be quite easy. But you know the assumption, central limit theorem, it will be approximate. The answer will be approximate. Okay.
Yes, sir.
Suppose you ask me, I want to go from A to B. How much time it will take? You ask me. I will say I don't know. Okay, that is better. Or suppose it takes 10 minutes time, I'll be able to say it might take around 9 minutes or 11 minutes. Something is better than nothing, right?
Yes, sir.
Even this is not something, this is almost everything. If little bit is not there, 99% is there, what is the problem?
Yes, sir.
So we need to know the distribution x bar. The only difference is distribution x we know. Now here we'll not use this one. We need to know the distribution of x bar.
Sure.
Yeah. So what is the distribution of x bar?
Mu comma sigma square by n.
Right. So that will be 165 mu divided by sigma square.
By n.
Yeah, by n. So 5 square divided by 50. So here the distribution of x bar will write, that will be normal 165 and this is half, right?
Yes, sir.
25 divided by 50. So here when I find this one, probability x bar greater than 165, x bar is itself a random variable.
Yes,
so
sir.
normally what I do is, because all the time students make a mistake, I change x bar to y so that you can directly find the value of this. You will not mind, you will not worry about central limit theorem. Directly you will be able to find this answer.
Yes,
Yeah.
yes, like before we did. Okay, sir.
This is y. Now we want y greater than 165. So we'll apply again the standardization technique. 167 minus 165, and we have to divide by square root of whatever is this one. This is sigma square. We'll write 1 by 2 here. And that will be equal to,
Sir, one doubt, sir.
yeah,
Sir, that the half is sigma square by n only, no? That is not a he if while converting to the normal standard normal distribution, we have to divide by only sigma, no? But that half is sigma square by n value, no, sir?
see, if you go deeper, okay, there will be deep problem. That's why I changed x bar to y. Why we are going there? Now y is a random variable, right?
Okay. Okay,
So
sir.
you forget about all this. We write x follows normal mu sigma square.
Yes, sir.
And let me write x bar follows normal mu sigma square by n.
By n.
Even I can introduce another one. This is not okay. Wait a minute. Yes. This follows normal n mu n sigma square. Now we standardize this one, how we write x minus mu divided by sigma follows normal 0, 1. That is standard normal distribution.
Yes, sir.
Then we say z follows normal 0, 1. Suppose you want to standardize this one. This one also I can standardize. I will write mu divided by sigma square by square root of n. Then this will turn to a standard normal distribution.
Okay.
This will follow normal 0, 1. Now, if you want, you can do this way. If you remember, suppose I will treat this as a random variable. X bar is also a random variable. So I will write this as, suppose, capital sigma square.
Okay, okay, sir.
Where capital sigma square is small sigma square divided by n.
Okay.
Then what I will write? My life will be easier, a bit easier. My life will be a bit easier.
Yes, sir.
Sigma.
Okay.
Even I can make it much easier. Lot of the difficulty will disappear. Even I can make this way. I can make this easier by writing a new variable. You can forget about what happened before. Just now you concentrate. You have a new random variable y. We don't need any central limit theorem. Forget about that. Y follows normal mu capital sigma square. So I'll start from y, and then comparing this, I will say that this will follow a normal distribution.
Okay, sir.
Yeah, even this one also, I'll write this distribution I have. I'll write z follows normal. I have n mu now. I'll make capital mu, where capital mu is n mu, and capital sigma square is equal to n sigma square, the whole n sigma square. If I can make this, then it will exactly follow the way I've written in the middle, because this is what important.
Okay, sir.
It's not that in central limit theorem these are not useful, because this is the base, right?
Yes, sir.
Follows normal 0, 1, and this will be my standard normal. Okay, so let me write instead W, because we've already given a symbol Z for standard normal. So alternatively, if I don't want to lose the symbols, I can continue with this. I can always continue with this. I can write this summation x or xi, whatever you want to write, n mu n sigma square. Then I will write summation xi minus n mu divided by this sigma will be small sigma square root of n sigma square. That will follow standard normal anyway. And this is my z. That's all. Normally, when I do the problems, I always say to do this way so that it will not create a problem. So z is greater than 2 divided by square root of 2. That will be 2 square root of 2. 828. Okay, so 2.8 I will take. But yeah, 828 also we can find. 82 we have.
Yes, sir.
83 we can take. 828 means 83 we can take.
Yes, sir.
If you want exact, can you find for 2.828?
Interpolation.
Yeah, interpolation. It's very small. When the height of the students in a class follows a normal distribution of a mean height of this and standard deviation this, why in this question we have this normal distribution?
Yes.
Do you think if I erase normal distribution condition, still it will work? But we have used normal here, right? Normality.
Yes, sir.
So that means if we take out the normal distribution condition, we still be able to do 2, but not 1. Because we use normality in part 1. In part 2, we don't need this one. If I write any distribution, this is not required. Any distribution, I can write a star distribution. Any distribution. I don't need to know what kind of
distribution is not necessary, sir.
Yeah, X bar, because our subject is X bar. We are interested in X bar only.
Okay, sir.
So why to see X when X bar is the subject? Target to X bar directly.
Okay, sir.
Do you need any assumption of X when you are dealing with X bar?
No, sir.
No, right?
Yes, sir.
Okay.
Population distribution is not that
not
much
required, right?
You said in the first last class.
Yes. So that is why what we need is we need to know the distribution of X only for part 1. Part 1 we have already done it. It's not a new one. We are not interested. Yes, I combined both so that I had to write the normality condition for the population, but it's not required for part 2. So when we are interested only in part 2, we don't need the normality condition. This will work. These 3 lines if we write, then we'll write part 2. Because we are in central limit theorem now, this will still work. So instead of part 1, I can change it and I can write another question. Because that part we have already done, we can make it this way. We'll write the same 50, or maybe let me write 60. 100 students are selected at random and their heights are measured. I have to find the probability that some of their heights, some x or some xi, whatever you want, you can write greater than 16700. This probability I need to find. Yes, sir. So suppose this is the first guy I selected. I have to measure height. This is x1. The second guy I selected, I have to measure the height. This is x2. The 100th guy I have to select. The height is 100 x 100. You have to find the probability that x1 plus x2 plus x100 is greater than 16700. So it's quite difficult to do this one directly. Even if I write 2, then it brings complexity. Forget about writing 100 and finding their mean. So we'll use central limit theorem. For central limit theorem, you need to know the distribution of summation x or summation xi. Directly you can write summation x. And that will be n mu n sigma square. N is 100 mu. So mu is 165. So this will be 16500 n mu n sigma square. N is 100, mu is 165, sigma square is 25. And mu I have written here n sigma square. Okay, n sigma square will be 2500. So I have to write here. Let me replace this one by another random variable so that it will be easier for me. I will treat this as a normal random variable x type. W is greater than 167. That is what I need to find. So I need to know the distribution of W. Distribution of W is normal 165, 2500. 16500, 2500. Then what will happen? I need to subtract 165. This one also I need to change. So this will be 16500, 16700 minus 16500. And here I have to change it. 2500 I'll write 50. I have to write 50 here. Now this is my standard normal. This is my standard normal. And I have to find 167 minus 165, that is 200. 200 by 50 is 4. Still it will be 1 because it's quite high now. If I make it 166, suppose. If I change the question, okay, let me write 1. I mean, if you find the answer is still 1, there is a 100% probability. So without finding 100% or 0%, there is 0% probability you will get 0 because it's greater. This will be 0. Now you want to get some answer, then you have to make it 166. Some answer you will get 166 if you write. Then what will happen? This will be 166. This will be 166. This will be 166. And this will be 166. Then 100 divided by 52. Probability z is greater than 2. That is 1 minus probability z is less than or equal to 2. And then this one will be
0.97725.
0.97725.
Yes, sir.
Okay. 0.97725.
1 minus.
Yeah.
$0.02275.
Okay.
Yes, sir.
This is how we apply central limit theorem directly. This is part 1 of central limit theorem. Now, if you go to part 2 of central limit theorem, I don't need to do any problem now. This much is sufficient. Now, if I want to do part 2 of central limit theorem, in part 2, what we will do? Part 2 will not apply directly central limit theorem. You see, I'm using the distribution of x bar and some distribution of summation of x
Xi.
greater than or less than, or even I can find summation x. Things we can find using central limit theorem. Now in part 2, this is part 1. In part 2, we'll not use central limit theorem directly. There the distributions will be given, binomial, Poisson and all that. We'll see that a normal distribution, a binomial distribution, we can approximate to a normal distribution. Poisson distribution, we can approximate to a normal distribution. Gamma distribution, we can approximate to a normal distribution. Log normal distribution, we can approximate to this distribution. So all the distributions we have, they will approximate to a normal distribution, because this is the main idea, getting a normal distribution, and then you will be able to solve problem. There will be some problem like when you are approximating the discrete ones to continuous one, when you compare to the continuous one to continuous one. So we need continuity correction. So all that will take one class.